Welcome to Data Science 1, Probability, Discrete Bivariate Example. I've been promising you an example here, so here it is. I'm going to do it in two parts. The first one is discrete. The second one is for continuous. Now, if you've had enough of the calculus, you can just watch this one and then skip the continuous one. But the continuous one shows you a lot of the mathematics that you need to know in order to be able to function well in probability. So if you're learning about probability and you're learning about mathematics, those are good things to watch. All right, things to remember: joint distribution, marginal distribution, conditional distributions. Well, not so much conditional today or in this video, but expectation, variance, and covariance. Here's our formulas for our expectation, variance, and covariance. Notice I also have the shortcut formula. So here's the definition of variance, and here's the shortcut formula. Here's the definition of covariance right here, and here's the shortcut formula. So I'm going to be using the shortcut formulas because it'll take way too long to work through all of this and keep the video at a reasonable length. All right, so we're going to go back to this distribution again. We've been looking at the grades and gender, and so we already have the marginals for X and Y, so we can actually do this. I'm not going to show you how to get the marginals again because they're in previous videos, but they're pretty easy to get. So let's consider X first, and here we go. Here's the marginal. We can calculate the expected value of X. Mu of X is equal to the expected value of X is the sum across all of the X's of X times the density or distribution F of X of X. So that's just 1 times the probability, plus 2 times the probability, plus 3 times the probability, and so on. And when you do the calculation, you're going to end up with 2.253. Now, I'm going to put the answers up here as we go along because we're going to be accumulating these so we can put everything together at the end, and we'll have all the pieces along the way. So here is the marginal for Y, if you remember. And so this is really easy to calculate because we just have two numbers, 0 and 1, and they both have the same probability. So mu of Y is equal to the expected value of Y. Same formula. This time we're summing across the Y's. So it's 0 times the probability plus 1 times the probability. So 0 times a half plus 1 times a half is a half. So that's pretty straightforward. All right, now we want to get the variances. So I'm going to use the shortcut formula. So I'm going to need X squared here. The shortcut formula is down here where the answer is, but I'm going to need the expected value of X squared, which is wherever I had an X, instead of just plugging in X, I'm going to plug in X squared. So it's going to be 1 squared times the probability, plus 2 squared times the probability, plus 3 squared times the probability, plus 4 squared times the probability, plus 5 squared times the probability. Put all that together, add it up, you get 6.609 for the expected value of X squared. Now, you feel like you're done, but you're not, right? Because we're using the shortcut formula, we have to put this extra piece in. So we're going to have our 6.609 minus the mu of sub X, and we're going to square that. And then we're going to end up with 1.1533. This is a measure of how spread out things are. It's in squared units, but you can take the square root and kind of get a flavor for what it does. Okay, do the same thing for Y. So here we've got the same setup. Here's our marginal distribution. Calculate the expected value of Y squared. Wherever we have in here had a Y, we're going to do Y squared. 0 squared times the probability of 0.5 plus 1 squared times the probability of 0.15 or 0.5, and we end up with 0.5. Okay, then we put it in our formula because it feels like we're done, but we're not. The expected value of Y squared minus mu sub Y squared is 0.5 minus 0.5 squared, which is equal to 0.25. All right, so boy, in the last 4 minutes, we've been able to crank through 1, 2, 3, 4 of these. Pretty straightforward. So they're not that hard to calculate. This one's the most involved one, but it's really not that bad at all. Here we're going to have to calculate the expected value of xy, which means we're going to have to use the joint distribution here. So every place that we have and we move along, we're going to multiply it by both x and y. So the first one is going to be x is equal to 1, y is equal to 0 times the probability. X is equal to 2, y is equal to 0 times the probability. X is equal to 3 times y is equal to 0 times the probability. And so on as we go down through here until we have, 1 times 5 times the probability. And when we do all that and add it up, we're going to get 1.097. We're like, okay, that's not too bad. Feels like you're done. you're not done. You're using the shortcut formula. So we're going to put in here, we have to multiply or subtract off mu x times mu y. So I've got my number here that I just calculated, the expected value of xy, minus mu of x, which is 2.253, and mu of y, which is equal to 0.5, and this gives you negative 0.0295. And you're like, wait a minute, can this thing be negative? Yes, it can. Okay, and don't worry about it being negative. So we get to this point. Here we are. So what? I mean, that's our big question. So what? We've calculated a bunch of numbers, but what does this tell us? Well, these numbers tell us the balance points along each of the distributions, especially the marginals of each of the distributions. This tells us the spread, how spread out each dimension is. And this one tells us how x and y are related, sort of. What we can do is we can turn the covariance into a correlation. So if we look at the formula for correlation, rho xy is equal to the covariance of xy over the square root of the variance of x times the variance of y. So this is pretty easy to calculate once we have this. We just plug in the numbers that we have from above. So we have negative 0.0295 divided by our quantity there, and we're going to end up with negative 0.0549. This is our correlation coefficient here. It's not very strong, but it's a theoretical correlation even, right? Because we still haven't seen data. We're just calculating this off of our probability distributions, and our probability distributions represent our random variable, which represent the sample space for the experiment that we will conduct, even though we haven't conducted it yet. But we can learn all kinds of things about what to expect from our experiment, and that's what expectation's about. What can I expect from my experiment so that I can check to see whether or not that's a reasonable thought or not. So far we've gone over quite a bit of material in order to find the correlation between x and y. It's been quite theoretical. We got one more example video, and then we'll do the bivariate normal. I know I said it was going to be next, but I decided to break it into two. And then we will jump into where all of this comes together and make statistics begin. Okay, so we're going to sort of slowly leave probability and enter into statistics and have something to work with there. But right now, we're just going to jump into our next video, which is the continuous distribution. See you there.